How's it going, everyone? Mr. Geyser here with the extra lesson for our 12C. For this topic here, this is known as the masterclass or the capstone of everything we've previously learned from Unit 3.1 to Topic 3.12. If these problems here, you feel confident that you can solve these, you are ready for anything on our Unit 3. For this first problem here, in this lesson, we want to use we will solve these trigonometric equations using the identities from those previous lessons. In example 15, we want to find the solutions of the equation on the interval of 0 to 2 pi, and then verify our answer using a graphing utility. For this problem, we're given this sine of x plus pi over 3 plus sine of x minus this pi over 3 is equal to 1. Well, if we rewrite this equation a little bit, spacing it out, we can actually write this here as that product of sums, where it's that sine and cosine plus that sine and times cosine of those two angles from inside that argument. Same kind of thing here where this is going to be the product of differences, where it's going to be this sine of x times cosine of pi over 3 minus sine of pi over 3 times cosine of x is equal to 1. We'll notice that little pattern there where we have that negative sine of pi over 3 times cosine of x, and now positive sine of pi over 3 times cosine of x. And those two terms there, they cancel out. Since they cancel out here, we're now left with that sine of x times cosine of pi over 3 plus sine of x times cosine of pi over 3 is equal to 1. Since we have two of those terms there, we could just rewrite it as 2 times sine of x times cosine of pi over 3 is equal to 1. Notice that we actually have that value for cosine of pi over 3. We know that's just equal to 1/2, and luckily for us, we know that 2 and that 1/2 there simplify each other out, and we're left with that sine of x is equal to 1. Now this here is what's going to allow us to solve for our value of x. Where in this case, we're trying to find the inverse sine of 1 of x here. Well, we know that really only occurs in one location on our graph, where we know that that x value, that theta, has to be pi over 2. Now to verify these equations here, we're going to plug this back into these problems here and check it using our graphing utility, or our TI-84. We go to our TI-84 here, kind of tab up just a little bit. If we were to plug in that value of pi over 2 back into where that x is, we end up getting that value of 1. So we know for 100% we're absolutely right. Now we take a look back at our next couple of problems here. We're given example 14. We want to try and find the solutions of the equations on the interval of 0 to 2 pi, and then we want to verify with that same graphing utility for the problem of sine of 2x plus cosine of x is equal to 0. Well, first, let's just rewrite that equation real quick. And there's not a real great way to start this off, but we can separate that times 2x a little bit, where we can actually rewrite it as 2 times sine of x times cosine of x, that double angle theorem that we were looking at before. And now we need to try and combine that cosine of x. Well, actually, we can just undistribute that cosine of x from both of those terms, and now we're left with these two equations. Since we have these two equations here, we can solve both of these out. Where we're given this cosine of x is equal to 0, well, we could just rewrite that as inverse of cosine of 0 is equal to x, and find what that x value is. Well, that only really occurs in two different locations here, at that pi over 2 and that 3 pi over 2. Same kind of thing here for that 2 sine of x plus 1 is equal to 0 here. We're just going to solve out for that sine of x. We're going to subtract 1 to both sides, divide 2 to both sides, and now we're left with the inverse of sine of negative 1/2 is equal to x. And I know that only occurs in those two locations. So now we're given these four answers of pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. And to double check our answers, we can take these four answers and plug them back into our equation here, and then double check to make sure we get 0. And if we go back to our graphing utility, we can kind of notice here that we're plugging in each of those values. There's an error. So we need to make sure we have that times there. Made that little mistake. So now we have this first problem where we plugged in pi over 2, and we got 0. For that second solution, notice for 7 pi over 6, we end up getting this really weird answer of 1.5 e to the negative 13. And just to make some sense of that equation or of this problem here, e just means moving the decimal. Negative 13 means it's making it smaller. So technically speaking, this equation here is 0.000000000000015. So it's like so incredibly close to 0 that if you ever get one of these problems as an answer, or if you get one of these answers here for one of these problems here, just say it's 0. And we get these last two problems here where we plug in 3 pi over 2, we easily get 0. But when we plug in this 11 pi over 6, we do get 0, but because our decimal and because our calculators here are taking our decimal approximations, we get 2e negative 13, so we would just write that as 0. So we know that all 4 of these answers here are exactly correct. Now we take a look here at our next example of 15. We're trying to solve out sine of x times cosine of x is equal to 1/2 between that interval of 0 to 2 pi, and we want to use this double angle formula. The reason why we want to try and use this double angle formula is at the very beginning, there's no real easy way to try and solve out that sine times cosine here, where instead of just trying to use some tangent or cotangent or some weird theorem, what we could do is just multiply both sides by 2 for that double angle formula. Where when we multiply both sides by 2, we now know that this left-hand side here is exactly equivalent to sine of 2x. And that right-hand side of 1/2 times 2, well, that's just equal to 1. Pretty easy. We now want to try and solve out that x by taking the inverse sine of both sides. But notice this little problem. When we find that 2x is equal to, well, inverse sine of 1 is actually an equation. Remember these equations here where they occur multiple times across our unit circle? When we divide by 2 in this case, we get a small equation of x is equal to pi over 4 plus pi times k. For these equations here, remember that these help us solve out the problem without needing to really solve it. All we do is we take the equation itself, and since k can be any integer value, meaning -1, -2, -3, 0, 1, 2, 3, any of these integers, we just plug in some value for k. For that first problem there, for when k is equal to 0, well, pi times 0 is just 0. So we know that that first solution there is exactly pi over 4. We know that for this second solution here, pi times 1 is just going to be pi. So pi plus pi over 4, placing that over 4 would just be 4 pi over 4 to get that solution of 5 pi over 4. But notice for this third problem here, when we multiply 2 times pi, we get 2 pi. And when we add these together, it actually goes over that restricted domain given to us. So we get 11 pi over 4, which is outside the domain, meaning that the only 2 solutions for this problem are pi over 4 and 5 pi over 4. Now, for example 16 here, we want to solve the equation of cosine of 2x plus 3 times sine of x minus 2 is equal to 0. And we're still trying to solve it between that interval of 0 to 2 pi. Well, let's first rewrite the problem here. When we're rewriting this problem, we want to try and manipulate it a little bit. Well, we can manipulate this cosine here of 2x. That's going to be one of our double angle theorems. We can bring in any of those 3 solutions or 3 equivalent equations for cosine of 2x. The equation that I would use is that 1 minus 2 sine squared of x. That way I'm just dealing with sine instead of cosine and sine. Once I have this here, I can just take that 1 and that -2 there, kind of simplify it out real quick. So I get -2 sine squared of x plus 3 times sine of x minus 1 is equal to 0. Notice this next trick. I don't really want to have a negative leading term here. So I can use that positive negative equivalency where I'm really just multiplying everything by -1. So all my negatives turn positive, all my positives turns negative. And now, well, notice again, we kind of have a binomial or a polynomial where we have like a square here, a single term here, and a constant here. Well, we can use that u theory where we now have u is equal to sine of x, and we can say 2 times u squared minus 3u plus 1 is equal to 0. Well, we know how to solve these problems. And as a reminder, if we ever have a leading term for that square value, meaning a is greater than 1, all we really do is take this a and take this c, we multiply them together, and we still solve out that x factor here, where we try and find those two values that multiply to give us 2 and add to get negative 3. In this case here, it's going to be that negative 2 and that negative 1 here. Once we have these, wherever we're plugging in this 2 into these parentheses here, we want to divide that constant by the value that we multiplied in the very beginning. So we take this minus 2 and we divide it by 2. When we divide it by 2, we end up getting 2u minus 1 times u minus 1 is equal to 0. Well, we're going to bring out that sine of x back into those u's there. And now we have these two equations that we want to try and solve. We'll bring that line down the middle. We want to try and solve out that left-hand side. Well, to solve out that left-hand side, we're going to add 1 to both sides, divide by 2, and eventually we'd get sine of x is equal to 1/2. And we want to try and find the inverse sine of that 1/2 and locate where that is on our unit circle. Well, we bring that over to here. We know that this occurs only in 2 different locations on our unit circle, where it occurs at that pi over 6 and that 5 pi over 6, making sure to leave a little bit of space for that one answer, bit of a foreshadow for the solution for this right-hand side of sine of x minus 1 is equal to 0. Well, we can solve this pretty easily by just adding 1 to both sides, and we take the inverse of both sides to end up getting this x is equal to inverse sine of 1, where we know that that only occurs in one specific location where it's at that key point of pi over 2. Now, we could check all 3 of these answers by plugging them into a graphing utility, but we actually know for all 3 of these, we didn't happen to square any values or do anything along those lines, so we know that these 3 problems are our solutions. Let's take another look here at example 17, where in example 17, we want to try and solve the equation of sine of x minus cosine of x is equal to 1 between that interval of 0 to 2 pi, where there's not a real easy way to try and find this. We don't have too good of a way to try and format this. You know what? Let's just square both sides. Let's just go down this random path. If we square both sides, we end up getting sine squared minus 2 sine cosine plus cosine squared is equal to 1. And if we were to rewrite this just a little bit using that associative property, we end up with sine squared of x plus cosine squared of x minus 2 of sine x times cosine of x. Now we're getting somewhere, okay? So we know that this first problem right here, sine squared of x times or plus cosine squared of x, well, that's just our Pythagorean theorem. We know that's equal to 1. So let's just subtract that 1 to both sides real quick. So now we're just left with negative 2 sine of x times cosine of x. Let's use that positive negative equivalency. As a rationalization for this, if we were to bring this out to the side here, all we're really doing in this case is we could add the whole term from one side to both sides here, and we just get 0 is equal to 2 sine of x times cosine of x. Really, these two equations here are perfectly equal to each other. We now want to try and solve out this here by seeing that 2 sine of x times cosine of x is just that double angle theorem. And we can say that this is equal to sine of 2x here. And we just take the inverse of sine of both sides, and we get 2x is equal to sine of x of 0. But notice one thing here. Remember back when we were writing these equations for these problems here? We know that inverse sine of 0 occurs in 2 different locations, at 0 and at pi. So when we bring these 2 equations from this inverse sine of 0, we know that it can equal 0 plus 2 pi times k, or pi plus 2 pi times k. For both of these equations, we're still going to divide both sides by 2. So we get x is equal to pi times k, and x is equal to pi over 2 plus pi times k. And eventually, what we could do, same thing for that previous problem, is we could bring this here and solve out, plugging in 0, 1, and 2 into both of these equations, and eventually, we'd find that we would get these 4 solutions. But notice, if we plug in these 4 solutions back into our problem here, we actually get 2 of them that don't equal 1. The reason why 2 of these solutions out of these 4 don't actually give us the equation we want is because they're extraneous answers due to the fact that we squared both sides at the very beginning. Now, in general, we need to square both sides at the very beginning to solve out the problem. So we can still square both sides. This isn't like a wrong thing to do, but when we do this, we need to remember to check all of our answers because sometimes it gives us extraneous problems. Well, finally, we'll take a look here at our final example in all of topic 12, the capstone, the hardest equation of solving out the equation of sine of x minus root 3 times cosine of x is equal to 1. For this problem, we're still using that interval of 0 to 2 pi, or we can rewrite it on both sides here. And we're still left with another one of those problems where we're not exactly sure what to do on both sides. So let's start playing around with it. In this case, I'm going to move that root 3 onto both sides here. So we have that sine of x is equal to 1 plus root 3 of cosine. Well, let's use that kind of same trick as before. Let's square both sides of our problem here. When we square both sides, we actually get sine squared of x is equal to this term over here. We just unfoil it. But what's exciting is we know that that sine squared is actually equal to 1 minus cosine squared. And that just comes from our Pythagorean identity, where we just subtract any one of these trig terms from the other side. We just get 1 minus one of those trig terms squared equals the other trig term squared. So now we just have cosine in all of our terms here. Well, let's just subtract all of these right-hand terms from both sides here. We don't really have room here, so imagine we're subtracting it. And eventually, we get negative 4 cosine squared of x minus 2 root 3 x squared plus 0 is equal to 0. For this, we can first try and simplify it out by a little bit by removing that 0 here, but we actually want to use that negative positive equivalency just so we're not dealing with a negative 4, that leading term in the very beginning. And from this here, let's just pull out a cosine from both of those terms there, and that gives us our 2 equations, where that first equation in this polynomial is this cosine x, and that second equation is just equal to 4 cosine of x plus 2 root 3. Easy. For that first equation there, we know how to solve out those problems. We just need to take the inverse of cosine on both sides, and we just need to locate when cosine is actually equal to 0. Well, we know that's going to occur in those 2 key locations at 0 and pi here, or at pi over 2 and 3 pi over 2. We know it occurs at those 2 locations there. We take a look here at that second problem. To solve this out here, we're going to subtract that 2 root 3 on both sides. Simplify it out a little bit more. We're going to divide by 4 here to get that cosine of x. Then we take the inverse of cosine on both sides. And we know when cosine is that negative root 3 over 2. We know that occurs in those 2 locations of 5 pi over 6 and 7 pi over 6. Now, eventually, we would plug in these 4 problems here back into the original equation and to see which one of these 4 give us 1 here. When we do that, we only see that these 2 answers of pi over 2 and 7 pi over 6 are the only 2 solutions because 3 pi over 3 and 5 pi over 6 are extraneous solutions due to the fact that we squared both sides in this solve here. In this final example, we showcase nearly all of the knowledge that we have in all of Unit 3. In that previous example 17, we even used that U method that we solved out earlier on at the end of Unit 2. For these problems, if you feel confident that you can solve these types of problems, you are more than ready to take on our AP exam. If you have any questions about any of the questions or any of the problems we did today, you can leave your questions down in the comments down below. And I look forward to seeing all of you guys in class. Take care.